Exercise 5D, log laws. So today what we're going to do is learn about using logarithmic laws to be able to simplify and solve equations. What you need to be able to do is recall the logarithmic laws and then apply these laws to simplify and to solve various equations. So this you already learnt last year, so we're going to do just a very quick revision over the laws. One of the most important laws, I often just call it the swappy rule, is this one here. So it's understanding what is a log in relation to an exponential, and you can think of it as just the opposite. It is the inverse of it. So we know that if we have something to the power of another number, so I don't know, it could be anything 2 to the power of 3, that would equal to 8. Well, what the log does is it sort of leaves a question mark. So log ay is equal to x. What that's saying is a to the power of what would give me x, and that what is on the other side. That's what you're solving for. So in this case, I can rewrite this as log 2 to the power of what would give me 8. And so that what is 3. So you can see it's asking a different question. Here it asks for the answer, whereas here it asks for the power. And that's what the log is. It's just the inverse. It's just asking, well, what is the power? So this swappy rule is very useful in being able to find what the power, the appropriate power would be to be able to give me this value inside as the answer. Here's another bunch of log laws that are going to help you in simplifying and solving equations. You will notice that all of these are the opposite to our exponential laws. So the first law, for example, for exponential is if I multiply two of the same base, I add the powers. Whereas here, what you'll notice is that if I add two logs together, then I multiply that inside value. So it's the opposite. So that's our first one. Our second one, very similar. This time, if I subtract the two logs, I divide the inside value. So again, opposite to my exponential rule where I have to divide first and then I would subtract my powers. Now, number 3 isn't necessarily in itself a law. I would think that the line number 3 actually tells me about this rule here, which I'm going to call number 3, but I'm going to use this concept of this line here to be able to explain how we get rule number 3. So what this is saying is that log a 1 on n. What happens? How can I simplify this? Well, the first thing is that using law number 2, we can see that I would have log a 1 minus log a n. My question is log a1, can I solve this because I have a number? Remember, your exponential is asking the question, a to the power of what gives me 1? That's the answer to this. A to the power of what gives me 1? Well, we know that anything to the power of 0 will always result in an answer of 1. So log a1 is equal to 0. And in fact, this is your first side rule that I want you to know. Anything that has an inside value of 1 is 0 because a to the power of 0 will always give us 1. So that's the first thing. That's 0. So that's negative log an as my answer. So what I can see is that log a1 on n is equal to negative log a n. What relationship does this have? Well, I can rewrite 1 on n as n to the power of negative 1. And so what do we notice? The relationship is here. I've just taken the power out the front. And so instead of having to do all of these steps to be able to get to this answer, I can just use this concept that I can take the power out the front of any value on the inside, and that is an equivalent logarithm. And that's what law number 3 says. So that's what it has here. Log a n to the power of m is equal to m log a n. So all that's happened is I've taken out the power, and this here is just the explanation as to why that is the case. As I just previously said, there are two other things that I want you to do. They're not necessarily laws, but just very important values. The first one is this here, as I've already explained, log a of 1 is always equal to 0, because the only way I can get an inside value of 1 is a power of 0. And the other one is log a of a. So if I have the same value for my base and the inside value, well, again, the question is log or a to the power of what gives me that exact same number? And the only answer to that is 1. A to the power of 1 will give me a. So these two, they're not laws, but they are two very important logarithms that you need to remember that are going to help you simplify equations. And this should be everything that you need to know. Let's go ahead and start simplifying some expressions. So example 10, part A, simplify log 10 5 plus log 10 2. We already know from our rules that when we add two logs, all we have to do is multiply the inside. So that's log 10 10, and we also know that if it has the same base and the same inside value, then that will be equal to 1. Part B, this time we are subtracting. We know that if we subtract, what we're going to do is divide our inside value. So that'll be log 4, and once again we find ourselves in the situation where the base and that inside value is the same. So once again that's equal to 1. Part C, log 216. This one's a little bit interesting because there's no other logs there, but I do want to simplify it, and I really want to use this law. You can see already how many times it's popped up. Log AA is equal to 1. So what can I do here? Well, can I write 16 as having a base of 2? Yes, I can. How does this help me? Well, now I can use my law where I can take that number out the front. So that would be 4 log 2, and I know that log 2 is equal to 1, so that's 4 times 1, so my answer will be 4. Now this is the long way of doing it. In general, what you can do is recognize that this will be 1 and the power is going to drop. So we can actually write our answer is equal to 4, and in the future that's what I'll be doing. Part D. So I've got 3 logarithms. Some are being added and some are being subtracted. So what this is going to result in is very large numbers. I can see 27 times 9 then divided by 81. It's going to be a little bit yuck to solve. But what I can also recognize that all 3 of these numbers can be written as a base of 3. Now how does this help me? Well, let's start by writing out the base. So that's 3 cubed. That's another way of writing 27. I can rewrite 9 as 3 squared, and I can rewrite 81 as 3 to the power of 4. Now, how does this help me? Well, I can use exactly what I did in part C. This is going to be 1, this is going to be 1, this is going to be 1, and what is going to be dropped is my power. So that'll be 3 plus 2 minus 4, which will be equal to 1. So that's a neat way of being able to work that out. So there are a bunch of examples of simplifying. What we're now going to do is use all of these concepts to be able to solve. So example 11, solve the following equations for x. So what we want to be able to do is get x by itself. I can see that I have logs on 2 sides. So what I want to be able to do is to try and get, just like with exponentials, the same base. So in this case, I want to get the same logs looking at both sides. What I want to do, first of all, well, just to clarify what I mean, I want log of something equals to log of something, and then that way I can equate what is in here. So how can I do that? Well, I want to try and get these logs in together, so by simplifying them. The first thing I'm going to do is use the opposite of our rule by bringing that power up to the top, and that can just remain as it is. And then I can again simplify by 2 logs subtracting. That means I can divide what is on the inside. And now hopefully you can see this scenario here. What I can do now is equate the insides because the outsides are the same. They're both log e of something. If that is equal to each other, then the inside must likewise be equal to each other. So that's going to be x squared on x minus 1 is equal to x minus 4. What I'm going to do is I'm going to take this to the top, so that'll be x squared is equal to x minus 4, x minus 1. I'm going to go ahead and expand that, so that'll be x squared minus x minus 4x plus 4, and then I'm going to simplify it all. So, I can take the x squared to the other side, so that'll just cancel out, so that will just be 0. So that's 0 equals, and then that's negative x minus 4x, so that's going to be negative 5x plus 4, and then I can solve for x from there quite easily. So I will take the 5x to the other side, so that'll be 5x is equal to 4, and then I'll divide both sides by 5, so my answer will be 4 on 5. Part B. What I can see here is I've got some logs, which includes x, and then some numbers. So I'm going to use the classic algebra rule, get all the x's on one side and all of the numbers to the other side. At the same time, I'm also going to take the powers to the top here, just to make my life a little bit easier. So I'm going to leave the 2 on this side, and I'm going to take the log 10x to the power of 3 over to this side. When I take it over, of course, it's going to be subtracted, plus 5 log, well, actually, if I'm going to have the power, that'll be log 10x to the power of 5. Now, I know these logs look like they're being added, but they are actually being subtracted because it's this one minus this log. So I might just write it that way just to make it look a little bit easier. Minus log and then I can go ahead and divide my logs, or the inside values of my logs. So that would be log 10 x to the power of 2. Now what do I do in this case? We come to our first use of our swappy rule. So what we're asking here is 10 to the power of what gives me x squared, and what this is telling me is it's going to be 2. So that'll be 10 to the power of 2 is equal to x squared. This is actually really nice because this time the powers are the same, but the bases are what's unknown. So if the powers have to be the same, well then that means x must be equal to 10. Another way to think of it is I can just take the square root of both sides, and that leaves me as x is equal to 10. Next one. Here we can see that we've got multiple logs, so we're going to do something very similar to our first example where we were able to try and make them look the same. So again, I want log e of something is equal to log e of something, and in that way I can equate the insides. So I'm going to take this power up to the front again, so this time it'll be x plus 2 squared. You just want to be careful in that what's being squared is the bracket, not the actual log. So if you just want to be super clear about that, you can write it like this, and then minus log ex is equal to log e3 x minus 1. Subtracting, which means I divide the inside, so that's x plus 2 all squared divided by x is going to be equal to log e3 x minus 1. And now that I have this situation here where I have the two logs, they are the same, that must mean that the insides are the same as well. Just to make that very clear, I can put brackets there as well. So because they are equal, that means the insides must be equal to each other, and then it's very much what we had done earlier. So what I'm going to do now is I'm going to expand. At the same time, I'm going to take the x up to the top here. I might do that first just to make it clear. Now I'm going to expand, so it'll be x squared plus 4x plus 4 is equal to 3x squared minus 3x. And I'm going to take all the x's, well actually I'm going to take everything to one side because it looks like it's going to be a quadratic. I'm going to take everything to this side so I can end up with a positive x squared. So that'll be 3x squared minus 1x squared, that'll be 2x squared. Then I have minus 3x minus another 4x, that'll be negative 7x, and then I'll have a minus 4 on the outside. Because it is not a monotheistic, because it is not a monotrinomial, that means there is a number in the front. Sorry, I said monotheistic because I'm thinking of religion, which means one God, but in this case, we are looking at an a value that is not one. So what we have to do is think of two numbers. So two numbers that will multiply to give me what these multiply to. So that's 2 times negative 4, which in this case is negative 8. And then add to give me the middle number, which is negative 7. So what that looks like, it'll be negative 8 and then plus 1. So what I'll have to do, because there's a number in the front, I will separate the middle term. So I'll have 2x squared minus 8x and then plus 1x minus 4 equals 0. And then I can factorize by grouping. So here I can take out the 2x, so that'll be x minus 4 that's left over. And here I don't have to take anything out, it's x minus 4 that's left over. It's also getting a little bit messy, so give me a sec just to rearrange myself. I'm going to move this all over. And I'll move this information over as well. All right, back up to it. All right, so now what we can do, so we're at the stage where we're at x minus 4 plus x minus 4 is 0. Now I can pull out x minus 4 as a common factor. And what I have left over, there's no plus sign actually, it's just 2x, and then here it's a 1, so plus 1 equals 0, and then I can solve for x from there. So it's a bit of a long one, but that is how you solve algebraically, and also using our log laws. Part D, this one's a little bit of an interesting one because I can see that I've got a log that's squared, a log that is not squared. I know there's a power of 5, but that's to do with the x, not the actual log itself, and then a constant. So again, where have you seen this concept? Something that's squared, something that's to the power of 1, and something that's to the power of 0. And I know they're not in the right order, so first of all, let me rewrite it in a way that makes it very clear. So this one is nice and clear. I'm going to take this over first, and I'm just going to get rid of this, well not rid of, but I'm going to put the 5 out the front. oh, sorry, we're using a base of 4 this time. It's very common that you usually use a base of e, so be careful not to make that mistake. So I've taken that 5 out, and then I'm going to take the 3 over as well. So hopefully you can see this. We've got 2, we've got 1, and we've got 0. So that's the power of 1. Where have we seen this? Well, it's with a quadratic, and it's also very similar to our exponentials. So in the exact same way that we did that with our exponentials, we're going to let a equal to log 4x, and in this case, I can start to write this as a, and then I don't need it in the last one. So what does that leave me with? That's going to be 2a, and then there's a squared, plus 5a minus 3 is equal to 0. And once again, I've got a trinomial that does not have a 1 at the front, so we're going to have to do our rule. So that will be 2 times negative 3, which is negative 6. I need two numbers that multiply to give me negative 6 and add to give me positive 5 in this case, sorry. So that looks like it'll be 6 and negative 1. Once again, split the middle term. So that'll be 2a squared plus 6a minus 1a minus 3, and then I can factorize by grouping. Here I can take out 2a, and here I just need to take out the negative. Then I will factorize the a plus 3 out, and I end up with 2a minus 1 is equal to 0. I'm then just going to continue on this side and solve it. So here I get a is equal to negative 3, and a is equal to 1/3. But of course, I'm not solving for a, I'm solving for log 4x. So now I'm going to substitute that back in. So log 4x is equal to negative 3, and log 4x is equal to 1/3. Now, how can I solve for x, or how can I get x by itself? Well, by using our lovely swappy rule. So that's going to become the base on both sides. So that'll be 4 to the power of negative 3 is equal to x, and 4 to the power of 1/3 will be equal to x as well. I just realized actually that this is not a third, that this is a half. So if you were saying this whole time, hey, that should be a half, well, good work. Yes, indeed, it is a half. So that's a is equal to negative 3, and a is equal to a half. All right, now that we're back on track, let's solve what this looks like. So first of all, the negative means the 4 needs to come to the bottom. So it's 1 on 4/3 is equal to x, and then the half is just a square root. So just for simplicity's sake, I'll write it as a square root. 1 on 4/3 is 1 on 64. So that's the first one, and then x is equal to 2. As to why x would not equal minus 2, the only reason for that is because, and you'll see when we get to graphs, but the value of x cannot be negative because you can't take the log of a negative number. So when you need to take the square root and solve for only x, it must be positive. All right, we're getting to a more interesting example here. You might want to try and pause this and give it a shot yourself, because there's nothing really new here. It's just the fact that we're going to be using our log laws to be able to solve our equations. So give it a pause, and I will continue in a moment. All right, this says, if log 4 of p is equal to x and log 4 of q is equal to y, show that log 4 of that whole thing is equal to 3 minus 3x plus 3y on 2. So how can we solve this? Well, the first thing that I want to do is I want to start here, and I want to get to there obviously, but I mean, that looks pretty yuck. So let's start breaking it up using the various log laws that we know about. So the first thing that I can see is that I can separate both the numerator and denominator, and I can separate that because I know that logs that are divided are actually, or values that are divided, actually mean that the logs have been subtracted by each other. And just for simplicity's sake, instead of writing the square root of q, I'm just going to write q to the power of a half. The next thing that I can see is that even when I've simplified it, there's a little bit more going on. There's values that are being multiplied, and we know that when values are multiplied, then the logs themselves have been added. So in this case, that'll be log 4 of p cubed. Now, just be careful. I know that these are being added, but then overall, they're being subtracted. So, I mean, I might just do this just to make it very clear as to what's happening. So we can put the bracket, or if you remember, then you can remove the bracket, but then the inside needs to be negative. Okay, so we're still not there because we need this log 4p and log 4q by themselves. We are getting there. The first thing is that this has neither a p nor a q, but that means that I can actually simplify it. So can I write 4 as 4 to the power of something? Yes, I can. That's 4 to the power of 3. Let's get rid of the 2. I'm going to take that out the front. So that's 2 log 4q. Then here I'm going to do the same thing. I'm going to take the 3 out the front. So that's log 4p. And then here I'm going to take the half out the front. Log 4q. All right, so what do we have left over? Log 4 is just 1, so that will bring the 3 down. Here, log 4q, as we can see up here, is equal to y, so that's y. That'll be 2y. Minus, then log 4p, as we know, is x, so that's just x, that'll be 3x. And then plus 1/2 log 4q, as we've already discussed, is y. So that'll be a half y. And now I can just put them all together. So I have a 3 that's just hanging out. Then there's a minus 3x. I'm just trying to copy the order that's in there. And then 2y plus a half y is going to be 3, minus, because I'm expanding that negative in. So it's 2y minus a half y will be 3 on 2y, as required. So it's a little fun exercise there as a puzzle. I hope you enjoyed that. All right, a few more to go. Example 13, solve the following equations for x. This is very similar to something we've already done, but you'll notice that we're going to get to a point where our simple exponential laws are not going to help us, and we will need to use our log laws to be able to solve it. So we can see that this is our classic 2x, 1x, no x, so that means we will let a equal to e to the power of x. That means I will have a squared minus 8a plus 15. This should be a very nice trinomial to be able to solve. So two numbers that multiply to give me 15 add to give me negative 8 are negative 5 and negative 3. So it'll be negative 5 and negative 3. And that means a will equal to 5, a equals 3, but of course I'm not looking for a, I'm looking for x, so now I need to sub that back in. So e to the power of x is equal to 5, e to the power of x is equal to 3. Now, when we did this before, what happened was that it was very easy to make the base the same, so it was quite easy to solve, but in this case, as you can see, we can't do that. So we need to be able to take this base to the other side. And how do we do that? Well, using our log laws, of course. So our swappy rule, which comes into handy so well, that'll be log e5. And now I've actually been able, that's a 3. Now I've been able to solve for x. Part B, you'll notice, is going to be very similar again. We've got our 2x, no x, 1x, no x. I do want to take everything over to one side though, just to make my life a little bit easier. And we're going to let a equal to e to the power of x. So that'll be 2a squared minus 9a minus 35. Again, we've got a number in the front, so what we want to do is multiply this out. Two numbers that multiply to give me 2 times 35, which is 70. And then two numbers that will add to give me negative 9. So these two numbers are going to be negative 14 and 5. Negative 14 plus 5 is negative 9, and negative 14 times 5 is going to be 70, rather negative 70, because that's a negative there. All right, what we're going to now do is split this up, so that'll be 2a squared minus 14a plus 5a minus 35 is equal to 0, and then I will factorize by grouping, so that'll be 2a, a minus 7, and then I'll take the 5 out, that'll be a minus 7 once again. These two terms are the same. And now I can solve. As always, I'm not solving for a, I'm solving for x. So I'm going to now substitute e to the power of x back in. And I'm going to use my beautiful swappy rule to help me take the e over to the other side. So x is going to equal to log e7, and x is going to be equal to log e negative 5 on 2. Now, this answer is correct, it's all good, but we do have an issue with this answer here. Now, previously I did say that you can't take the log of a negative number, but why? If we think about it, e to the power of what gives me a negative, or if we want to think about anything more simple, so let's just use 2. 2 to the power of what will give me a negative number? Let's say -1. Well, there's actually nothing that I could ever put a number to another power that is going to give me a negative result. Even if I put it to a negative power, for example, all that happens is it goes to the bottom. So there is no number that I can put to a negative number that will, no number that I can put to a power that will result in a negative number. So that's why the log of a negative number is always undefined. And so my only answer is x of log E7. That was a long exercise, but you did it. We're at the end of exercise 5D.